Hello, in today's video we're going to look at properties of pure substances, and those pure substances, we're going to look at them based on intermolecular forces. So, we'll look at properties of pure substances based on intermolecular forces. Okay, so many of our properties of our pure substances are going to be based on intermolecular forces. So if we have weak intermolecular forces, then our dispersion forces, especially if we have weak dispersion forces, are going to be considered weak intermolecular forces. Anything that has weak intermolecular forces, we're going to have lower melting points and boiling points. So these are going to be things that only exhibit dispersion forces, and those dispersion forces are going to be weak because they are going to be low molecular weight. So these are going to be things that are usually gas at room temperature. And like I said, these are going to be things with small dispersion forces. So they're going to be low molecular weight. Okay. And we can kind of increase our intermolecular forces. We're going to go with medium intermolecular forces. And these are going to be things with medium melting points and boiling points. Okay. So these are going to usually be liquid at room temperature. And these are going to be things that have medium dispersion forces, or they're going to have dipole-dipole interactions. They're going to be like medium molecular weight or exhibit dipole-dipole or hydrogen bonding. Okay. If we have strong intermolecular forces, right? So here we have substances that are going to have large melting points and boiling points. So these are going to be solids at room temperature. So for these to be solids at room temperature, we generally have to have very large molecular weights. So we have strong dispersion forces. Or significant hydrogen bonding. So we have to have several hydrogen bond acceptors and donors within the molecule. Okay? So just in general, looking at intermolecular forces, we can kind of guess what state of matter we're going to be in. But we can also look at other properties based on intermolecular forces. And we're going to look specifically at properties of pure liquids today. We will look at solid properties in the next chapter, but we're going to look at pure liquids in this chapter. So we're going to look at three properties. We're going to look at viscosity. We're going to look at surface tension. And we're going to look at capillary action. Each one of these are going to be affected by our intermolecular forces that we've talked about in our last video. So first let's look at viscosity. And this is the resistance of a liquid to flow. So I've got a picture down here real quick so we can look at what viscosity looks like. So water, not very viscous. Milk, a little bit more viscous. Oil, even more. As we get into syrups, we get even more viscous substances. We look at different types of oils. So things that flow very easily are going to be low viscous. Things that have a hard time flowing would be considered higher viscosity. So what is it that changes our viscosity of a substance? So if we have molecules that can flow past each other very easily, we're going to have low viscous substances. So high viscous substances are going to be ones where the molecules don't flow past each other very easily. What happens is these molecules are going to kind of get entangled within each other. So, think about things that get entangled. Generally, we think about long, stringy type things, right? If you've ever had a bunch of string usually gets very entangled very easily. Noodles, long, skinny, very easily entangled. So we're looking at high molecular weights, high surface areas are generally things that are going to have greater viscosities. So we're mainly looking at dispersion forces when we're thinking about viscosity. Yes, if we have dipole-dipole interactions or hydrogen bonding, that will make something more viscous. But looking at water, it has a very strong hydrogen bonding, but it is not very viscous because it's not a very large molecule, right? It's not going to entangle very easily. So we need intermolecular forces that are going to cause entanglement, and generally we think about dispersion forces when we're looking at that. Okay, so if you have greater surface area, larger molecular weights, you're going to have a greater viscosity. Next, we want to look at surface tension. So our surface tension is going to be the energy required to increase the surface area of a liquid by a unit area. Okay, so I'm going to show a picture again real quick. If we think about the surface of a liquid, on the surface, or the surface molecules, they are going to be they will have a net pull down, as we see here. Actually, let's do that to the side. A net pull down by the molecules in the bulk liquid, because there's intermolecular forces pulling them down. At the surface, there is nothing pulling them up because there's no intermolecular forces between air, which is a just dispersion and very weak dispersion forces, versus a liquid which generally has a lot of intermolecular forces going on, like dipole-dipole interactions and hydrogen bonding. So there's going to be a net pull down on those molecules. That net pull down will actually cause it to decrease the surface area and get what we call surface tension. So that net pull down makes it harder to have the liquid expand. We see the same thing when we have a bubble, right? So if we have a liquid bubble, the gravitational force is going to try and push it down, but in general, it's going to want to beat up because it's going to have the center of that bubble kind of pulling everything towards the center and causing that bubbling surface. You will see if you have a surface that is attracted to it, will kind of wet the surface a little bit more, and it'll have a greater or a less surface tension because it's got a pull in another direction. Okay, so we've got surface tension is going to be based on a downward pull. This downward pull decreases the surface, and that is what we call surface tension. Okay, and this is, in order to kind of stop that surface tension, we have to add in energy to either expand or to break through a surface. So if you've ever seen things like really light objects, such as a paperclip or a bug, just kind of stay on the surface without breaking through, that's all due to surface tension. So they're light enough that the effect of gravity is not strong enough to break that surface tension. Okay. The last property we want to look at is capillary action. And in order to look at capillary action, we have to look at cohesive and adhesive forces. So a cohesive force is an intermolecular force that binds similar or same molecules. And then an adhesive force is an intermolecular force that binds substances to a surface. Okay. So, capillary action is an interplay between cohesive and adhesive forces. So, what happens, capillary action itself is, as a definition, the rise of a liquid up a very narrow tube. So, what I mean by that interplay between cohesive and adhesive forces is, we can see this when we look at a capillary. So, as a substance has cohesive forces, it's going to have surface tension going on. But then it's also going to have adhesive forces, which is going to cause it to want to go up a surface. So we're going to have cohesive forces beating up, and then adhesive forces causing a meniscus, right? So we're going to have these two things going on, our cohesive and our adhesive. So this is cohesive. This is adhesive. So this is the tube walls, if you will. So the cohesive forces are going to pull the molecules down. The adhesive forces are going to cause the molecules to go up. And we're going to continuously do this until gravity outweighs both the cohesive and the adhesive forces. So when we have a smaller amount of liquid, gravity is not going to affect it as much. So we'll have a higher rise of that liquid. And then as we get a larger and larger tube, a wider tube, gravity is going to have more effect and it's not going to go up as great. Okay, so those are the properties that we wanted to look at today. That's going to be the end for this video. See you guys later.